Good morning students. Welcome to 13th video on system of particles and rotational motion. In this video I am going to discuss an important 3 marks question, that is conservation of angular momentum. So they may ask question like this: illustrate the law of conservation of angular momentum. If this question is asked along with a statement of conservation of angular momentum, so then it would be a 5 marks question. In that case, they will ask question like this: state and illustrate law of conservation of angular momentum. So statement carries 1 mark and remaining 4 marks is given for the illustration of conservation of angular momentum. So we know that angular momentum of a rigid body capable of rotating with respect to an axis of rotation is given by L is equal to I omega, where I stands for moment of inertia of a rigid body and omega stands for angular velocity. In order to say the angular momentum of a rigid body rotating about an axis remains constant, if moment of inertia increases, then angular velocity decreases so that its product remains constant. On the other hand, if the moment of inertia decreases, then angular velocity increases so that again in that case also their product remains constant. So let us illustrate this conservation of angular momentum with an example of a girl sitting on a rotating chair. So consider a girl sitting on a rotating chair in which the axis of rotation is passing through the center of the chair. So initially, if the chair is rotated such that if her both arms are outstretched, the chair is rotated such that initially if both arms of her are outstretched like this, then because the both arms are away from the axis of rotation in which she holds these masses on her hands, then moment of inertia is very large. Therefore, she performed the rotation with a less angular velocity. Because moment of inertia is more in that case, therefore angular velocity is less. While rotating, if she slowly brings back her both the hands very close to her body, then she may be able to rotate with larger angular velocity. So this is because when she stretches her hands inward very close to axis of rotation, in that case moment of inertia decreases, then angular velocity increases so that their product remains constant. So in both the cases, what we saw is the angular momentum remains constant. Initially she rotated such that both her hands are outstretched. So the moment of inertia is very large, angular velocity is less, so their product remains constant. So therefore angular momentum remains constant. When she brings back her both the hands very close to her body while rotating, then she may be able to spin with a very large angular velocity, because at that time moment of inertia decreases and angular velocity increases. Even in that case also the product remains constant, thus the angular momentum remains constant. We can see similar kind of examples in the swimmer who is on the springboard. If he jumps off from the springboard and he does many somersaults in air before he jumps off into the water, so this is called as springboard diving. In that case, you might have seen that the angular momentum is conserved. Even in case of a ballet dancer, in which a performer is performing large number of rotations in which she is capable of rotating on her toe. In that case, the angular velocity is very large and moment of inertia is very less. If the dancer stretches her arms outstretched with respect to axis of rotation, then the angular velocity decreases, because in that case moment of inertia increases. So thus in case of ballet dancing, a ballet dancer in which she may be able to rotate with respect to an axis, the angular momentum is conserved. In case of springboard diver, the angular momentum is conserved. In case of a girl sitting on a rotating chair, the angular momentum is conserved. So this is the law of conservation of angular momentum. So thus angular momentum is conserved in all